Foundation of life on Earth. From the crops that feed us to the ecosystems that sustain our planet, healthy soil supports every living system. Yet today, agricultural soils across the world face unprecedented challenges. Climate change, declining organic matter, salinity, drought, and excessive chemical inputs are steadily reducing soil productivity and resilience. In countries where agriculture plays a vital role in food security and economic stability, these challenges are even more critical. Farmers are forced to produce more from less fertile land, while the cost of agricultural inputs continues to rise. In this global challenge lies an opportunity to rethink how we nourish our soil, using science, sustainability, and locally available resources.
This documentary presents a scientific research project titled Development of Organic Fertilizer, Humic Acid, obtained from lignite coal. The project was conducted over a 6-month period, from January to June of 2025, and was funded by the Enhancing Digital Government and Economy project, under the Bangladesh Computer Council and the ICT division of the Government of Bangladesh. With a total grant of $35,000, the research aimed to develop an efficient, affordable, and sustainable method for producing organic fertilizer from indigenous raw materials. At its core, this project explored a simple but powerful idea, whether lignite coal could be transformed into a high-quality agricultural input capable of improving soil health and crop productivity.
Humic acid is one of nature's most powerful soil conditioners. Unlike conventional fertilizers that directly supply nutrients, humic acid works by enhancing the soil's natural ability to support plant growth. It improves soil structure, increases water retention, enhances nutrient availability, and stimulates beneficial microbial activity. In crops, humic acid strengthens root development, increases nutrient uptake efficiency, and improves tolerance to abiotic stresses such as drought, salinity, and temperature extremes. These properties make humic acid especially valuable in modern agriculture, where climate stress and soil degradation are increasingly common. Despite its importance, commercially available humic acid products are often expensive and frequently imported, placing them beyond the reach of many farmers.
Bangladesh possesses reserves of lignite coal, rich in organic carbon and humic substances, yet this resource remains largely untapped for agricultural use. Traditionally, lignite coal has been viewed as a low-grade energy source. However, scientific research suggests that it holds significant potential as a raw material for humic acid production. This raised a critical question: can lignite coal be transformed into high-quality humic acid in a way that is efficient, affordable, and environmentally sustainable?
To address this question, the research team defined 4 primary objectives. First, to extract humic acid from lignite coal. Second, to compare 7 different extraction methods. Third, to identify the most efficient and scalable technique. And finally, to evaluate the quality of the extracted humic acid against commercial products. These objectives guided the design of a systematic and comparative experimental framework. To address this question, the research team defined 4 primary objectives. First, to extract humic acid from lignite coal. Second, to compare 7 different extraction methods. Third, to identify the most efficient and scalable technique. And finally, to evaluate the quality of the extracted humic acid against commercial products. These objectives guided the design of a systematic and comparative experimental framework.
7 extraction methods were selected based on scientific literature and practical feasibility. Each method differed in chemical reagents, pH adjustment, extraction time, temperature conditions, and purification techniques. The primary chemicals used included sodium hydroxide, potassium hydroxide, and nitric acid. Physical separation techniques such as centrifugation and filtration were also incorporated to enhance product purity.
Alkaline extraction formed the foundation of several methods tested in this study. Under alkaline conditions, lignite coal reacts with strong bases such as sodium hydroxide and potassium hydroxide. This reaction breaks down complex organic structures and releases humic substances into solution. Variations in chemical concentration, extraction duration, and agitation intensity were tested to determine optimal conditions for maximum humic acid yield.
Acid oxidation methods were also explored, using nitric acid to enhance humification. This process oxidizes coal structures, increasing the solubility of humic compounds. While effective, acid oxidation required careful control of reaction conditions to ensure safety, efficiency, and product quality.
To improve separation and purity, physical enhancement techniques such as centrifugation and filtration were applied. These steps allowed for better isolation of humic acid precipitates, contributing to improved consistency and analytical accuracy across all methods.
After weeks of laboratory experimentation, the results became clear. Among the 7 methods tested, 3 consistently outperformed the others. These methods produced higher yields of humic acid, deeper coloration, an indicator of higher humic content, and stronger positive reactions in standard humic acid tests. Other methods produced lower yields or required higher chemical inputs, making them less suitable for large-scale applications.
The most effective method utilized a 0.1 molar sodium hydroxide solution, combined with 24 hours of continuous agitation, followed by acid precipitation. This method produced the highest humic acid percentage among all tested procedures. The extracted product displayed dark coloration, strong chemical stability, and characteristics consistent with high-quality humic acid. Remarkably, the humic acid percentage exceeded that of several commercially available products.
Beyond laboratory success, this method offers strong potential for real-world application. It requires relatively low chemical concentrations, moderate processing time, and standard equipment, making it suitable for scaling up. By utilizing indigenous lignite coal, production costs can be significantly reduced, opening access to affordable organic soil amendments for farmers. The next phase of this research involves field-level validation. Planned agricultural trials will evaluate the impact of the extracted humic acid on soil properties, crop growth, nutrient uptake, and stress tolerance under real farming conditions.
This research represents more than a laboratory achievement. It demonstrates how scientific innovation can transform local resources into sustainable agricultural solutions. By developing an efficient method to extract humic acid from lignite coal, this project contributes to soil health, climate resilience, and food security. It is a step towards sustainable agriculture, rooted in innovation and powered by indigenous potential. Thank you.